My name is Yoochan, and today I'm going to talk about Pspray timing side channel-based Linux kernel heap exploitation technique. Reliable kernel exploitation is very important for attackers not to be detected by the defender. However, focusing on exploiting heap overflows and use after free, reliable kernel exploitation is challenging, as attackers do not have knowledge on the status of the kernel heaps. To address this issue, we developed a new exploit technique that utilizes a timing side channel-based timing side channel attack to identify the status of kernel heap. With this new technique, the attacker can launch reliable kernel exploitation. I think most of you are familiar with user applications heap allocator. User applications heap allocator use a heap area, and if there is no space, application extend the heap area to use the area. On the other hand, Linux default heap allocator SLUB uses a single unit called SLUB, which consists of one or more pages. There are many mechanisms in SLUB, but we will focus on two features that are important from exploitation perspectives. SLUB manages multiple slabs by dividing the slab into CPU and node. Each CPU has page and partial page, and node has partial page. The important thing to note here is that our object allocation is done by CPU's page, and the CPU's page can be changed to another slab under certain conditions. The second feature of the SLUB is slab release randomization. The old kernel allocates objects in order starting from the beginning to the end. However, with the randomized mitigation technique, the kernel randomizes the allocation order to prevent heap overflow vulnerability when the slab is created. These SLUB features make the heap exploitation fail. To be specific, exploitation fails when exploiting use after free and heap overflows. Now we will go into more detail about why these features lead to failures. First, we need to know how use after free exploit is performed. A common use after free exploit is to allocate a vulnerable object, then free the vulnerable object, and allocate a target object in the same address, then triggering use after free to corrupt the target object. At this moment, the important thing is that the vulnerable object and the target object are placed to the same address. As we mentioned, our object allocations are done by CPU's page. However, the problem arises when the CPU's page changes the slab while exploiting. For example, suppose that slab A already allocated two objects. If the system call allocate vulnerable object, the slab is fully used and moved to full list, then another slab is moved to CPU's page and allocate one additional object and freeing the vulnerable object. At this moment, if the attacker tries to allocate target object, the target object is allocated in slab B because current CPU's page points slab B. The key point here is that if the CPU's page changes during the exploit will fail. In addition, we need to know how heap overflow exploit is performed. Please keep in mind that this is the best scenario. A common heap overflow exploit is allocating target object and allocating vulnerable object. At this moment, the important thing is the vulnerable object and the target object are adjacent. However, since the attacker does not know the allocation status of the target slab, they don't know how many target objects are allocated in target slab. Therefore, there are cases that the target object is allocated in target slab but not adjacent because of mitigation, and the target object is not allocated in target slab. Then how to launch reliable kernel exploitation to avoid exploit failure in the presence of SLUB features? Let's summarize the problem. For use after free, the problem is that CPU's page keeps changing. This problem suggests that the attacker needs to know how many objects were already allocated. For heap overflow, the problem is that the vulnerable object and the target object are not adjacent. Similarly, this problem suggests that if the attacker needs to know how many target objects were allocated in the target SLUB. This requirement leads us to one question. What if the attacker knows allocation status of the SLUB? We thought this information would dramatically increase the reliability of this exploit. Therefore, we focused on how we can figure out the allocation status of the SLUB. Based on question, we developed a new exploit technique, Pspray. The key idea of Pspray is timing side channel attack. Linux kernel implements multiple allocation passes depending on the heap status. We found timing side channel to identify allocation passes by measuring the time taken to allocate. And this finding leads the attackers to know the allocation status of the kernel heap. Now let's see the allocation sequence of SLUB. As we already mentioned, all object allocation are done by CPU's page. Therefore, the fast pass is allocating an object from CPU's page. If there is no SLUB in CPU's page, CPU's partial page is moved to CPU's page. If the CPU's page and partial page is empty, node's partial page is moved to CPU's page. And if there is no SLUB in CPU and node, the kernel calls body allocator to create a new SLUB and moves to CPU's page. Here, we predict that slow pass would be very slow because it creates a new SLUB through the body allocator. Here is the POC of Pspray, that is the timing difference between passes. The x-axis is allocation trials and the y-axis is performance measurements. We allocate an object 1,000 times. From the figure, you can easily notice that the time performance differs between the slow pass and the other passes. As we already mentioned, USENIX fails because CPU's page is changed. Here's how to apply Pspray to USENIX. First, using Pspray, we found when performance of allocation system call differs with the others. At this moment, since the slow pass is executed, the kernel has a new SLUB with one allocation. Then we allocate n-1 spray object to fill the SLUB. This is to assign a new SLUB to use for the exploit. Then the SLUB A moves to full list. After that, if the user allocates one object, then a new SLUB will be assigned. Then triggering the system call which allocate vulnerable object and additional objects. Then freeing the vulnerable object. And since CPU's page is not changed, we can allocate the target object to the same address. We mentioned that the main problem of heap overflow exploit is that the vulnerable object and the target object not being adjacent to each other. Here is how to apply Pspray to heap overflow cases. First, using Pspray, the attacker can notice when a new SLUB is created. Then the attacker allocates n-1 spray object to fill the SLUB. This is to assign a new SLUB to use for the exploit. And corresponding SLUB is moved to full list. Next, allocating target object, then the kernel creates a new SLUB and fill n-1 target objects. The reason for allocating only n-1 target object is to ensure the last spot is reserved for the vulnerable object. Lastly, allocating one vulnerable object. Then the vulnerable object and the target object are adjacent. The only possible exception case would be when the vulnerable object is in the last position of this SLUB. However, we will discuss in the evaluation, it is very unlikely to happen. we evaluated 6 use-after-free vulnerabilities. The baseline for the use-after-free vulnerability was tested with simple deallocation followed by target object allocation. The test achieved 70% success rate. However, after applying Pspray to the mechanism, the success rate dramatically increased to about 100%. We also evaluated for 4 heap overflow cases. The baseline for heap overflow was tested using heap function. The test indicated 30% success rate. However, after applying Pspray, the success rate also dramatically increased for heap overflow cases. Please note that even with Pspray, the success rate does not reach 100% is because the vulnerable object may be placed at the edge of the SLUB. Lastly, we also developed mitigation against Pspray. The key idea of mitigation is adding a new slow path. First, creating a new SLUB, randomly pick one object. Next, when picked object is allocated, the kernel checks CPU's partial is empty. If CPU's partial is empty, the kernel calls for the allocator to create a new SLUB and move to CPU's partial. Since origin slow path use created SLUB immediately, we can notice when a new SLUB is used. While since the new slow path puts new SLUB in a CPU's partial page and use it later, we cannot predict when a new SLUB is used. For the conclusion, we introduced a new exploit technique which combines previous exploit techniques with timing side channel attack. Then we proved our attack technique is effective with 10 vulnerability cases. We also suggest the mitigation for Pspray that successfully conceals when a new SLUB is used. Lastly, we believe this type of logical flow can also exist in other kernels as well, because many developers do not consider the side channel attack when developing software. This is the end of my presentation. Thank you for listening to the presentation. And now we would like to move on to the Q&A session. Are there any questions?